record the session. All right, here we go. So let us, let me go back to this one more time. This is the method that they call the method of consistent deformation. A method of consistent deformation. And the condition here that we can add the displacement together and result in zero. This is what we call compatibility. Okay. And I don't remember the name. Oh, okay. And this equation sometimes is called the compatibility equation. Okay. So the method of consistent deformation, we use the compatibility equation to solve for the extra unknown. And once we can determine one extra unknown or two or three or four, our structure becomes determinate. Okay, let's say if you can solve the reaction, you now have this is your beam, right? And then instead of writing support now, I have just another force acting on that location. So this is basically a determinate structure now, and you can proceed to finish your analysis once you have obtained this one. Okay, so let us look at this. You guys got the file now, right? Hello?
Yes.
Okay, so if you are curious about the calculation, so let us try to consider this delta B. Okay, if I want to calculate delta B, my bending moment diagram is clearly looking like this. And this value is minus WL squared over 2, correct? And if I am going to use M over EI diagram, I should divide this by EI. And if I want to calculate displacement at B, the easiest way I can do is by using the momentary method. And that becomes my elastic curve. It's a bit too big. This distance, if I call this A, if I call this B, this distance, which is delta B, is exactly TBA. So I can go ahead and calculate deflection at B, which is equal to TBA, and it's the moment of this area with respect to point B. So the area is 1/3 of WL squared over 2EI multiplied by the length, which is L, and then take the moment of this moment diagram with respect to point B. This distance is 3/4 of an L. So multiply with that. So 3 is gone. Correct. Okay. Yeah, 3 is gone. Now you have 4L and then 2 multiplied by 4, that's 8. So it's in fact WL to the power 4 over 8EI. Did I get it right in the lecture? Oh, I already erased it. So, okay, that's the number. So oh, it's gone again. You can see that. Oh.
Can you repeat?
Okay. The channel is gone. Happens a lot today. Okay, so here it is. This is your moment area. This is maximum value, WL square over 2, right? And to calculate the displacement here, if I use the moment area method, it's exactly equal to TBA. And TBA is the area of this, which is 1/3, multiplied by the height, and then multiplied by the base length. And then the moment arm is 3/4 of an L, because we take the moment with respect to B, so multiply by that. So in the end, I get this. In fact, it's a negative value, which shows that it's a downward displacement. Okay, so that means I can easily calculate this, but that's not the point. Okay, so if I again instead of having this, I now write this structure and ask you to calculate the reactions. That would mean that you can now break this into the structure with the uniform load that has a displacement delta B, and then another structure with the reaction at B that will cause the displacement. I will have to use this notation delta BB. You can directly calculate delta B because this is what it is. That's your delta B, right? But you can also calculate your delta BB here, but the answer will be in terms of RB. And you can therefore establish your compatibility equation saying delta B plus delta BB equal to 0. I can easily go ahead and calculate this because you see that this becomes my bending moment diagram. That value is RB multiplied by L, correct? And again, delta BB is equal to the area, which is a half. The height is RBL. And the base is L. We take the moment with respect to B. So the moment arm of this triangle is 2/3 of an L. So I multiply that with 2/3 of an L. 2's gone. So now, and I should divide this by EI as well. RBL over EI. Okay. So this becomes RBL cubed over 3EI. And when I add them up, oops, I'm sorry. When I add them up, I will have minus WL to the power 4 over 8EI plus L cubed over 3EI multiplied by RB. Write this form so that you can see RB as our target equal to 0. Okay. Something missing? Okay, no. So we can solve this. And now see RB is equal to WL to the power 4 over 8 EI multiplied by 3 EI over L cube. That is entirely gone. This is just power 1, EI is gone. So the answer is 3W L over 8. So you see, it's no longer half-half, like a simple beam, right? So for anyone who doesn't do this and say, oh, must be equal, reaction, this is completely wrong. So the idea is to try to set up this equation and to try to set up this compatibility equation. Compatibility, you need to fill this with first deflection caused by the reaction, then second deflection caused by the actual load. Okay, this is how we can use the calculation of deflection to solve the indeterminate structure. Okay, and I am going to stop about the indeterminate structure here, and then I will reverse the course to the calculation of deflection. But I begin with this so that you know where we are headed. Okay, the final destination is to solve the indeterminate structure by using this method of consistent deformation. And in doing so, you must be able to calculate the displacement. So, that is why I am saying that after midterm, things get more spicy. You need to be able to calculate displacement in order to solve the indeterminate structure. Okay. Now let us see another one. Okay. Say I'm gonna look at this one. Now, okay. If I have a basic simple beam like this, generally without anything, at midspan, your beam is going to come down like this, right? And you will have the midspan deflection. But things would change. Let's say if I introduce another support in the middle, when it was a simple beam, you would have the midspan deflection. But when another support is added here, you can no longer have the midspan deflection. In other words, I could say that this is not like a real situation, okay? I could say that this reaction RB must produce the same deflection as this uniform load. Okay, whatever this delta midspan is, this must be equal to the displacement caused by the reaction at B, so that you can truly have this situation where you have three supports. In other words, when you have this beam, you can break this beam into this one and that one. So let's say if delta midspan is known, you can solve for delta BB can be obtained. How can we obtain that? We obtain this by establishing the compatibility equation. I can simply say delta B or delta midspan plus delta BB is equal to 0. That becomes our compatibility equation. And that is also one extra equation that we need to solve the indeterminate structure. This extra equation will give you that extra reaction. And once that extra equation is no longer an unknown, you are now dealing with a basic determinate structure, but with that load. So it becomes something like this. After you solve for RB, you now have this. And then with the value of RB, which you already know how much it is. So I will have the situation where I can give you this displacement first, or I can give you the equation, the formula that you can use to calculate this. With that much information, you should be able to obtain the RB. Okay, likewise, let us consider this frame. Okay, if that's the frame, and you will see that this frame is going to move here, right? So let's call that delta D in the horizontal reaction is given if you know this value. And I am asking you to take a look at another frame. Same dimension. But instead, this support becomes a hinge. How are we going to solve this? I can easily remove this HD, right? Horizontal reaction. Once I remove this, my frame will look like this. And because I remove the reaction, what I will obtain is the displacement. When there is a reaction, there is no displacement. Once I remove the reaction, I will have the displacement, just like before. In this condition, you know, if I remove this reaction or support, I will get the delta B. If I have it, there is no delta B. And likewise here, if I have a simple beam, if I remove the support in the middle, I have delta in the middle. So when I consider this, I know that if I look at this determinate frame, I have this displacement. So it's like a twin with this structure. In this structure, this one is indeterminate. Okay, but when I remove this reaction, when I remove this HD, when I remove this, I will have displacement instead. And if I can obtain how much this displacement is, I can also establish the compatibility equation to solve this frame, right? Hello, that it is an equation. I'm not, that's in the a question, not equation. Okay. Well, senior should be okay, but junior, hey, hello.
Okay.
You okay? Generally, if I was in the classroom, every year I would have to explain this like 2 or 3 times. And this, if we were to solve this frame, we need to modify it by removing the reaction so that we have this frame that we can calculate this displacement. So if this is your indeterminate structure, you remove the reaction, one reaction, so that it becomes a determinate structure. This is also called a primary structure. Okay? But the point is, if you can calculate this, this will be equal delta D in the horizontal direction caused by this load will be equal and opposite to, say, delta DD in the horizontal direction caused by HD. Okay? Or we can wrap it up and say that delta D plus delta DD H is due to HD is equal to 0. So we need to fill in this equation by the values of displacement coming from this primary structure due to the load, and then coming in from this one due to the reaction, which should come from something like this. And then HD. It's gone again. Happens a lot. Can I do this right away? No, it wouldn't allow me. So I have to stop the sharing and then share it again. Okay. Okay, so this comes from this. Okay, so that is the concept of, you know, the method of consistent deformation, or sometimes they simply call that force method. Okay, this is compatibility equation. Oh no. The method itself is called the method of consistent. Here we go again. Consistent deformation or the force method. Any question? Hello? Any question, folks? No? Coming from the chat. No, I suppose. Okay, that's not a question. So guys, you want me to repeat on anything? I will leave the indeterminate structure for now, because I have shown you that you need to be able to calculate displacement to solve the indeterminate structure. So we are going to go through the calculation of displacement or deflection now. Okay? Is that any question? I suppose not. Okay. So I think we are gonna get into something more serious, slightly more serious. Okay. I have a page left. Now you can see we are gonna go through a lot of calculation of displacement. You can see that the displacement of the truss. So, you know, let us switch to the handout. Okay, we have mentioned this indeterminate structure. So we're going to go through chapter 5. Calculation of displacement. Where's the beginning? I think so. It's here it is. Okay. So, you know, you can read this blah, 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 but, you know, so that you know, we sort of have the calculation of displacement in this class simply because we need to use it to solve the indeterminate structure. But in fact, the calculation of displacement is one important aspect of civil engineering because of the so-called serviceability. When you design the structure, okay, there are two parts that you need to consider. The first part is the strength. As you have learned from the mechanics of materials class, of course, your structure must be strong enough. Whether or not you go into structure itself, in hydraulic structure, in geotechnic, okay? We all need to consider the strength of the material. And then another one is called serviceability. Because if you have too much deflection in the structure or whatever it is, you may have, you know, the non-structural elements, you know, being damaged. Because as I say here, your windows will crack. You cannot open the windows. You cannot open the door. You know, the sliding doors become stuck, and people will ultimately feel unsafe. And if the deflection becomes too much, the structure will fail. Because let me try to explain another situation to you. Let's see if some of you can grasp this. You know, in design of the building now, say under the earthquake will come through the ground, right? So that the force coming from earthquake is introduced into the building in the form of ground motion. And then it can be converted into some kind of shear force acting at every level of the building, like that. Now the concept that they generally require engineer to design the building is that we no longer design the building by using the elastic method. So that means when the earthquake hits your building is going to take some damage. If you design the building not to have any damage at all, you will end up with a very, very big structure. And you should know that the earthquake force doesn't come every day. Sometimes it comes once in every 10 years, sometimes one every 25 years or so. So to design the building to withstand the force that occurs in 50 years is not a very smart idea. So they would allow the building to have some damage. And in doing so, they will allow you to design the building based on the deformation. So your building will deform. But if the deformation becomes too large, your building will become unstable. So you need to increase the size of the structure to try to reduce the deformation. But still, we don't design it in the elastic region. So that is the design completely based on deformation. They use deformation to judge the stability of the building. This is still far away from you now, but it's just another very important aspect of the calculation of deflection. Okay. Okay, this is like a little bit of a gimmick, not pleasing. You go back home and you see that the ceiling of your house is coming down poorly, badly. You don't want to, you know, you're not going to be happy, right? And here, this is true, very true, and many of you will face this. Deflection must be satisfied in many operating flow. Okay, some of you may go on and design or construct the factory, and they call factory because they have machines in there, and some machines cannot be operated when the floor deflects down too much. So the design of the floor must be controlled by deflection as well, to make sure that the machine can operate effectively. You know, if this one is not controlled correctly, when you use the machine, the floor will vibrate a lot. And if you can recall the steel stairs at the KFC, the not the Kentucky, right? The KMUTT food canteen, like that. You know, when you walk on the stairs, you know, to that leads you to the door, the way that connects to the CVE3, it vibrates, right? That means probably the calculation of the deflection is not, you know, well taken care of. And deflection in roof system is controlled to prevent the non-structural component damages, such as the ceiling and stuff. You know, this is another thing in structure. Skip that, okay? Sometimes the temperature will cause excessive deflection as well. This does not happen quite extensively in Thailand because it's like hot and hot. But sometimes it may, because let's say, for example, you design the bridge that is surely going to be exposed to temperature. You may need to check the effect of temperature on the deflection of the bridge. Okay, and vibration, I already mentioned that. And you know, in the US of A, they prefer the steel structure a lot. And steel structure, you know, they come in piece by piece and you connect them. So the structure as a whole is not as solid as concrete, but concrete is a weaker material. So if you want to have the structure that can support the same amount of load, concrete structure sometimes is not viable as it becomes too big. So they prefer the steel. But the steel structure, because it's not, you know, entirely solid, so it could have deflection. And especially, you know, somewhere like Broadway, you know, where they dance a lot, the human behavior can cause vibration, and we need to check that as well. Okay, and this is the last one, is the reason why we mentioned this. Okay, and all right, let's talk about this a little bit more because before we have another break. We have so many methods to calculate the deflection. You have learned this double integration method, where you write your moment equation, perform integration twice, you get the equation, the general equation for the calculation of deflection anywhere on your beam. This is a good method, very quick, but it cannot be used to calculate deflection in the frame. Another one is the momentary method, which I just used to solve the deflection in the beam. Okay, it's a very ugly line. Okay, momentary method. But you know, the momentary method, you can actually use this to solve the deflection in the frame, but it's difficult because if you want to use the momentary method, you must draw the deflected shape to obtain the relationship of this, right? TAB, TBA, or whatever. If you don't have this relationship, you can't solve the deflection. So it's pretty good to use to solve the deflection of a cantilever beam, for example, because you know the deflection is incidentally equal to this T value. So it's very easy. But for a simple beam like this one, perhaps, this one, if you want to use the momentary method to solve this beam, you are going to have to, you know, okay, here's your beam. If you want the mid-span deflection, you need to draw the deflected shape and then do this. Your deflection is this one, but then let's say this is A, B, and then this is C. This becomes TCA, which is not the deflection. Then you have to calculate TBA, and the deflection becomes like this distance is half TBA, so delta mid-span becomes like TBA over 2 minus TCA, something like that. So it's kind of difficult, and not very welcome. Okay, that's the second one. You have learned this before, so I'm not going through it in details. Another one is the method of a conjugate beam. You want to know about it? In fact, I don't really, ask you to do any specific method when I give you the assignment. Generally, we don't focus on this conjugate beam method either, because as the name suggests, it's a beam, so it cannot be used to solve the deflection in frame. So I tend to skip this. But you should know that this method of conjugate beam is amazing, but it's a variation of the momentary method. Okay, if you have this from double integration, right? EIY is equal to deflection. You differentiate this, you get the slope, and then you differentiate it again, you get the moment. So when you do it from here, if this is equal to moment, you differentiate it once, you get a shear, and then twice you get the load. So if I put the bending moment diagram on the beam, for example, there. Okay, need another page. Sorry. Let's say if I have a simple beam with a simple load like this, my bending moment diagram is going to look like this, right? So if I put the bending moment diagram on the beam, let the bending moment diagram be the load on the beam. If I solve this beam, the shear at any location of this beam that has the bending moment diagram as a load. In fact, we call this a conjugate beam. Okay. The shear of a conjugate beam is, in fact, the rotation of the actual beam CVE of the conjugate beam. And if you cut the free body diagram and solve for moment of the conjugate beam, you can guess now that the moment is deflection of the actual beam. So it's kind of good for simple beam, because if you want to use it for the cantilever beam, more restrictions will apply. Okay, so like this, because say if you want to use the conjugate beam for a cantilever beam, this guy has a bending moment diagram like this. So conjugate beam, because a moment is equal to deflection, you have moment here, but the deflection here is 0, right? You have moment here, but in the real world, the deflection here is 0. So to use a conjugate beam right away is going to be wrong. So if you want to use a conjugate beam for the cantilever beam, you must swap the support condition. The free end becomes a fixed, and then the fixed, oops, sorry, it's the wrong side. The fixed becomes the free becomes a fixed. And then you have your bending moment diagram as a load. And it's just the same applies. Okay, so this is not going to be our predominant method. We are going to use another method that is called the virtual work. And ladies and gentlemen, in fact, you have also had that with Ajahn Chelaput before. I know that. All right. So is there any question? I suppose that's a no. So I am going to stop the record.